My name is Morgan. I'm Mrs. Smith's daughter.
Hi, Gustavo.
All right, everyone. I hope you liked Morgan's hello in the first slide. Tonight we're going to look at 3 last laws. The first 2 involve moles. And we're going to take a look at Avogadro's law first. This is the same Avogadro as Avogadro's number, which just happens to deal with moles. And so Avogadro didn't just limit himself to studying the number of atoms in a sample and helping us to develop Avogadro's number and the mole. He continued his work with gas laws. And he noticed that at a constant temperature and pressure, the volume of a gas is directly proportional to the number of moles in the sample. So here I have this diagram. Let's take a look. 1 mole of oxygen gas has 1 volume, and 2 moles is twice the size. And so this is a direct proportion. The volume and the number of moles are directly proportional to one another. And so we have the equation V1 over N1 equals V2 over N2. I'm not going to do an example problem on this because this is exactly how Charles' law runs. The only difference is instead of temperature, we're talking about moles. So when you run into a problem that's only talking about volume and the number of moles, and temperature and pressure are held constant, you know you have Avogadro's law. Here's the big law for the night, the ideal gas law. This law is another law that involves moles, but there's some more to it than just Avogadro's law. In order for the ideal gas law to work for us, we have to assume some things about gases that don't actually happen. An ideal gas, according to the scientists, does not compress into a liquid at low temperatures. We know it does. There's liquid nitrogen. It does not have forces of attraction or repulsion. We know that can happen, although it tends not to happen too often because of the collisions being elastic. And we are also supposed to assume that an ideal gas is composed of particles that have no volume. That's craziness because that breaks the definition of what matter is. But we have to assume these things in order for the ideal gas law to work. So when we do this, we have a law that has a mathematical relationship here between the pressure, the volume, the temperature, the number of moles of a particular gas, along with a gas constant. We call that an R value. This mathematical relationship is basically a snapshot in time of what a particular sample of a gas looks like at one moment. Nothing is changing. There are no 1s and 2s. It's just everything at one moment in time. And that law looks like this. PV equals nRT. You know you have to use the ideal gas law if nothing is changing and moles are also present in the problem. Or grams. They may give you grams or they may ask for grams, and then you have to do a calculation. Okay, so what about this R value? These are constant values that include every unit possible in the ideal gas law. So we've got units for volume, pressure, moles, and temperature here. And based on the pressure value, or excuse me, the pressure unit, we have 2 different values. There's more. There's an R value for every pressure unit. I just like to give 2, and you can always do a conversion if you need. The first R value is 8.314 liters times kilopascals over moles times Kelvin. This one involves the Pascal. So if the problem is involving pressure units of kilopascals or pascals, you're going to want to convert that pressure unit of Pascal to kilopascals and then use this R value. If the problem is talking about atmospheres of pressure, then you definitely want to use 0.0821 liters times atmospheres divided by moles times Kelvin. We're going to take a look at how this all works in the example on the next slide. All right, here's our example. So like usual, please copy down the example. All right, let's take a look. What mass of oxygen, here's our first clue that this is different than other problems that we've been doing this unit. We're looking for mass here. And we're asked, what mass of oxygen is required to fill a 10.0 liter tank? So there's a volume for us, 10.0 liters, at a pressure of 2.1 atmospheres and a temperature of 25 degrees Celsius. So here's how you know this is ideal. This is an ideal gas law problem because we're talking about mass, which means we need to get moles, and nothing's changing. We don't have two measurements of volume or pressure or temperature here. It's just a snapshot. Okay. Oh, I can't shrink that, huh? All right, well, we're stuck with that tonight. Sorry, guys. All right, so let's take a look at how we have to convert our Celsius to Kelvin. Remember, we add 273. So that makes it 298 Kelvin for us. Now we can write out the equation and solve. So we're going to start out with the equation PV equals nRT. This is the equation for the ideal gas law. We're looking for mass, okay? In fact, that tells us over here on our list that we don't know what N is because we need moles first in order to get to mass. So if we're going to solve for moles first in order to get to mass, we have to solve for N. So we're going to divide by RT on both sides. Our R and T's cancel out, and we're left with N is equal to PV over RT. Now we can plug in chug. As we start to solve this, let me move over. We have 2.1 atmospheres times 10.0 liters divided by, and now we have to use an R value from the last slide. Because pressure is in atmospheres, we're going to use 0.0821 liters times atmospheres over moles times Kelvin. And we're going to multiply that by 298 Kelvin down here, okay? Now, it becomes very important for you to keep in mind how you're going to type this in the calculator. You take 2.1 times 10.0 divided by, on your calculator, you're going to open a set of parentheses here, 0.0821 times 298. Okay? When you do this, you get an answer of N is equal to 0.86 moles of oxygen. If we go back up here and look, our atmospheres canceled, our liters canceled, and our Kelvin canceled, leaving us with only moles, which is what we were kind of sort of looking for. We're almost done now. We found moles, but the problem asked for mass. That tells us we're looking for grams, so we need to use the molar mass of oxygen. So we're going to do a quick conversion. 1 mole of oxygen to 32 grams of oxygen. Remember, oxygen is diatomic. And when we do this, ooh, the whole thing's going to shrink on us now. When we do all that work, we get 27 grams of oxygen. That keeps proper sig figs. And we're done with the problem. This is the last law that we're going to learn tonight. We're going to look at something called Dalton's law of partial pressures. This is a very easy law in concept. Of course, there's a way to complicate this law through our book work. But let's take a look at the law first. Dalton found, and this is the same Dalton from our first atomic theory, John Dalton, in the 1800s. But anyways, Dalton found that for a gaseous mixture, the total pressure of the system is equal to the sum of the partial pressures of each gas in the mixture. So what this means, if we take a look at this diagram here, we have a gas A in red and it's been mixed with gas B in blue, the particles in blue. If gas A has the particles of gas A exert their own pressure because they have their own molar mass and they have their own velocity. And so when they collide with the walls of the container and other particles inside the system, they're exerting their own pressure. Basically, they're their own chemical. The particles of B have their own partial pressure because they have their own molar mass. So let's say that A has a partial pressure of 1 atmosphere, and B has a partial pressure of 3 atmospheres. To find the total pressure, we simply add them together. And so the total pressure of the system is equal to 4 atmospheres. That, in a nutshell, is Dalton's law of partial pressures. And of course, as we get into the bookwork, things are going to get more complicated because our author is going to have us use the ideal gas law to find pressure for the different chemicals first, and then we can add. So there's different ways to do this. We can also be given the total of a pressure of a system and have to find one of the partial pressures. So then that would require subtraction. But our algebra skills are there. We can do that. I hope you guys enjoyed our talk tonight. I hope you liked listening from or hearing from the girls, and we'll talk about this stuff next week. Have a great night.